So here we have our random digit table. It's nothing more than random digits already pre-written for us. We can use this if we don't have technology at our disposal. We can do this, we can all do problems together. The AP people like to give these to us so that way we can follow our steps together. People did use these a lot more before technology was so prevalent. One can be found in the back of your textbook if you ever need one also. How is it used? Well, as I said, it's just a string of digits, 5, 6, 5, 9, 6, 5, 2. The only reason for this gap is because it's easier to group them on the eyes. Similarly, when you get to the end of the string here, 5, you jump right in with the 5 here and you keep going. I'd like to show how this is used, how we can use these by jumping into this problem. So how do we design a simulation using a probability sample space? That sounds fancy, but a probability sample space just means known probabilities ahead of time. How can we emulate that? Well, here are the 4 steps we're going to use to end up doing a simulation. As we're doing an explanation, we'll explain what we're using, for instance, if we're going to use a digit table, a number generator, or something else, and what you're doing with it, be literal. I usually make a key, so explain your key, how you're going to have the digits stand for something. That'll make sense as we do the problem. I'll come back. What do they stand for? How many digits are we going to use at a time? Are we going to allow repeats or not with our simulation? Do we have to ignore some digits? Some aren't going to be used. Be patient and thorough here, I say. Just think about how you're doing it so you should be able to follow your steps. You're basically telling somebody how to write a program for it and follow a step-by-step procedure. And you're not around to ask questions. Explain how to model the outcomes and what to record. So after we get these digits, what are we doing with them? Finally, identify when to stop each simulation. How long do we go until we're done? Here's a silly example I made up, a simulation example. Made this based off of how a lot of cereal boxes and other things have prizes in them, somewhat random. And I made this problem up a little while ago. Popular Kids cereal box contained either a Lance Armstrong card, 50% of the boxes have those, a Serena Williams card, 40% of the boxes have those, or a rare Tiger Woods card at 10% probability. When I made this up, it wasn't that long ago, but it's funny how much our impressions have changed of Tiger Woods, but especially Lance Armstrong. Serena Williams is much older now, but she's still pretty impressive heavy hitter. Explain how one could simulate the outcome of cards types. Let's say we're going to buy 14 boxes of cereal. So I want to say, well, what happened? We understand this probability, but what does it look like when you actually say buy 14 boxes? Is it really likely to not? Is it really likely to get a Tiger Woods card? We think we should get one, but what does it look like? Are we going to actually have 50%? Usually when these are done, they're done many times, simulations, to get a feeling of what different events could happen, to get a feeling on it. So how will we do this? Well, I'm going to use the random digit table. Let's go back and take a look at it. So what makes this problem an easier problem, the starter problem, is that the probabilities given are all varied by 10%. So they all jump by 10%. So we have 50%, 40%, 10%. Why I say it's easy is because, well, digits occur with 10% likelihoods, right? So what I could say is, every time I grab a digit, that simulates me going to the store and getting a cereal box. And if it has a 5, that'll be one type of card, or 9 might be another type of card, and so on. With this case, remember, 50% likelihood of Lance Armstrong. And so I might say, digits 1 through 5 would be Lance Armstrong, would represent Lance Armstrong. And I might say, digits, let me get these right. What I say, 1 through 5, so 6, 7, 8, 9 would represent Serena Williams, and I didn't mention 0 yet. Remember, so 0 could represent Tiger Woods, or any variation on like that. I usually think about my key first. I call that step 2, because when somebody's reading it, they'll look at that maybe next. But I'll mention that first. So how am I going to represent this? My key would say something like this. We'll let digits 1 through 5 represent Lance Armstrong. What I say, 5, 6, 7, 8, 9 represent Serena Williams. And 0 represent Tiger Woods. So that's how I'm using my key. Now what am I doing? Here's how I explain. Okay, I got my key ready. So here's how I might write this up. Right. Use a random digit table by choosing one digit at a time. Remember, each digit is going to signify the event of grabbing a cereal box. It might not, some other problem might need 2 digits, 3 digits based on the probabilities we need. So one digit at a time. I think about this. Am I going to allow repeats? Yes, if I get Tiger Woods on the first box, the likelihood of the next box is basically the same thing. Right, so I will say ignore repeats. You definitely would mention that. We don't have to mention repeats otherwise, but I'll be, just to be clear, allowing repeats. The other thing I made sure to think of is, am I going to be using all the digits? Yes, notice all digits are being used. You have the option to ignore digits. If I had something that went by ninths instead of tenths, I could say ignore 0. And every time we see 0, it's as if it's a blank slate not there. We'll look at problems like that later. If I think about that, that's what I meant by do we allow repeats or not? Do we ignore digits or not? Be thorough, think about those things. They can get you. Explain, step 3 was explain how to model the outcomes and what to record. So what are we doing? We're going to record the corresponding card type using the key. Finally, I have to have a stopping rule. When are we going to stop? According to this, one simulation stops after 14 boxes. So stop after 14. Call them card types. Card types. So that's what it would look like. Notice this is only one simulation. I could have a computer doing it by hand, takes a little while, but I could have a computer do this many times and that'd be just fine. So if you have this on your paper, I have this on mine, you can go back and do it with the table. So what will this look like? Let's take a look. So I'm going to go grab these digits one by one and see. So 5, that's Lance Armstrong. When we're grabbing this, we always show our work in there. So 5, Lance Armstrong. 9 is Serena Williams. 6 ends up being Serena Williams. 5 is Lance Armstrong. 2 is Lance Armstrong. 9 is Serena Williams. 1 is Lance Armstrong. 3 is Lance Armstrong. Lance Armstrong. Serena Williams. Lance Armstrong. Lance Armstrong. I have a Serena Williams and a Lance Armstrong, and we draw a little stopping arrow like that. That would be one simulation. If I had to do it 3 times, I would pick up right there and do another run like that. We noticed, I remember, if we had wanted to get a Tiger Woods card that only had a 10% chance, after 14 boxes, I didn't get one. I could say, well, apparently that can happen. We know that. This is just one example. So what would this look like? I would record it, and I would say, how many Armstrongs? 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 Armstrong cards. 1, 2, 3, 4, 5, 5. Serena Williams cards. None. 0 Tiger Woods cards. And that would be a simulation. I'd like to jump now to a little more involved problem. That's an interesting problem done as a free response problem a few years ago. Let's take a look. We call this the radio show problem. Every Monday, a local radio station gives coupons away to 50 people who correctly answer a question about a news fact from the previous day's newspaper. The coupons given away are numbered 1 through 50. With the first person receiving coupon 1, the second person gets 2, and so on until all 50 coupons are given away. On the following Sunday, the radio station randomly draws numbers 1 to 50 and awards cash prizes to the holders of the coupons with these numbers. Numbers continue to be drawn without replacement until the total amount awarded first equals or exceeds $300. If selected coupons 1 through 5 each have a cash value of $200. Coupons 6 through 20 have a cash value of $100. Coupons 21 through 50 each have a cash value of $50. All right. Read that as many times as you need to and pause correspondingly. A, explain how you would conduct a simulation using the random number table provided below to estimate the distribution of the number of prize winners. Notice the number of prize winners, not the how much you give away. And then B is asked us to perform the simulation 3 times. That is, run at 3 trials. Start at the leftmost digit, move across just like I taught. Mark your procedure clearly so somebody could follow you like I did. remember, we're going to report the number of winners in each of your 3 trials. So we only did our simulation, our trial, 1 trial for our simulation. In our other example, we would do this 3 times. So how will this look? You can pause and try this out. That'd be great. I'd like to go straight to the answer, though, to save time for me, I guess. Here's what your answer would have to have. Scheme. We would have to use a 2-digit random number from there. Notice how they were broken up. Remember, 00 would be like 100, 01 is like 1. So we could say something like, if it's between 0, 1, and 50, we'll use it to represent the selected ticket. Remember, there are only 50 tickets, so we'd say ignore 00 as well as 51 through 99. Stopping rule. Determine the amount of the prize associated with the chosen ticket and add this to the total amount so far. If the amount awarded so far is less than $3, repeat this process. That's unusual. It's not a certain, we don't know how many times it's going to take. We just do it as many times as we need. The count, we would note the total number of winners, and this should be in here somewhere, non-replacement. We would ignore any ticket that's already been awarded a prize. Notice if we got 02, and then again we got 02 later, we wouldn't count that. We would literally skip it as if those digits weren't there, and we would go ahead and run it. And then we'd repeat that as many times as possible. That's 1 simulation. They say note it's okay to devise a scheme that uses a 2-digit number to represent each ticket. For example, 01 and 51 representing ticket 1, 02 and 52 represents ticket 2, but it has to address the idea of which ticket is it and ignoring repeats. I think it's much simpler to just count 01 through 51 as 2 digits, meaning tickets, and ignore everything else. Let's take a look how we'd end up doing this. So what would this look like? I could show our work like this. Ticket 72, right, we'd ignore. Ticket 74 we'd ignore. Ticket 91 we'd ignore. We're not worried, there are plenty of digits. We have ticket 33, that is a ticket, right? So that's a ticket, and we'd end up getting, what, ticket 33 according to our rule. Remember what that ends up being. $50, right? So I'd say $50 so far. And then ticket 47 is also a winner, and that's another $50. And then, so I might say $100, which was how much so far. 65 is ignored. 03 is counted. That's that's more money, so that's $100. Or was that $200? So we have a total of $300 so far, $300 so far. We're not done though. We stop at $350 or higher. And ticket 30 adds another $50 onto it. So now I'm at $350, and I stop. So that'll be 1 trial, and I'm supposed to count how many tickets that was. And with my ignoring which ones I didn't count for, I didn't have any repeats, I ignored those 2, but I have 1, 2, I can look here, 1, 2, 3, 4. So I'd say after 1, we get 4 tickets. I was asked to run that 3 times, so I would run that 2 more times, just to take a look at how this would appear. So as we're grading this, they just did a couple of things. For your scheme, you'd have to have a clear, correct statement. You're welcome to pause this video and read this if you can see it. Hopefully it's showing up clearly. But this is how they would basically grade you as for your response problem. Since you're seeing this pretty early in the year, you can feel free to read this over. And for your response problems are graded out of 4 points. 4 points if you have essentially correct all 5 components. 3, substantial response, you have to have 4 out of 5. 2, you have to have 3 out of 5. 1 point if you have essentially correct on only component 5, because that's kind of seen as a separate entity. That's part B, if you notice. The other parts are all for part A. Essentially correct on the other 2 components, and that's how the scoring. I'll talk more about that scoring, but it's unusual scoring because they only have 4 points. Anyway, I'll end on this screen, especially since that bottom part is faded off a little bit there. And in a way, you can take a look at that more if you need to. Anyway, that concludes our section 1 of chapter 3.